All right, so to wrap up this lecture, we're going to talk about the Gaussian mechanism, which is sort of a kind of canonical epsilon delta differentially private algorithm. So in particular, what the Gaussian mechanism is going to do is it's going to be useful when we're adding noise to a statistic that outputs vectors in high dimension. It's often going to let us add significantly less error to those vector valued statistics. But we're mostly going to talk about it mathematically for the case of a real valued statistic because it highlights most of the relevant points and is easier to follow. So just to kind of refresh your memory, a Gaussian distribution is this classic bell curve, though it appears I've drawn it a bit asymmetrically because I don't have good drawing skills. And the distribution is parameterized by a mean mu and a standard deviation sigma. And we typically write the distribution n of mu comma sigma squared being the variance. Okay, so it's just common to write it in terms of the variance. And it has this funny looking density function where the probability density of an individual point y is proportional to e to the minus y minus mu squared. So the distance from the mean squared divided by 2 times the variance. Okay, so if you want to remember for comparison, for Laplace, we had e to the minus distance to the mean not squared. Whoops, doing that right. Just the absolute distance to the mean divided by lambda, which was roughly the standard deviation. And so the Gaussian mechanism is like we take that thing in the exponent roughly and we square it. And then we divide by 2, but that's a small matter. Okay, so the point is that the tails of the distribution drop off proportional to e to the minus distance from the mean squared. Okay, and one of the reasons the Gaussian distribution is nice is precisely because the tails of the distribution are thinner. So the probability of seeing very large deviations from the mean is smaller than it would be for Laplace. It's also nice because it just has lots of nice properties. It comes up in statistics in a number of ways for fundamental reasons. So it's also just kind of useful to be able to work with Gaussian distributions because they're just cleaner and better understood than Laplace distributions. Okay, so it's going to be important for what we do to kind of remember this density function. So if we have a real valued statistic, so just like in the case of the Laplace mechanism, we can look at some real valued statistic that maps data sets to a real number. And the Gaussian mechanism is to take this statistic, f, compute the true value f of x, and then add noise from a Gaussian whose mean is 0 and whose variance is set to 2 times the sensitivity squared times log 1 over delta over epsilon squared. Okay, so let's just unpack that for a second. So when we used Laplace noise, the standard deviation was proportional to delta over epsilon. And for the Gaussian mechanism, the standard deviation is also proportional to delta over epsilon, but with this square root of log 1 over delta factor. Okay, so maybe the first thing to notice right off the bat is this is actually worse than the Laplace mechanism in terms of privacy and standard deviation. But as we'll see, it'll be useful when we want to output statistics in high dimension. But for now, we're not really gaining anything. We're just going to analyze this mechanism just for the sake of convincing ourselves that it's another way of achieving epsilon delta differential privacy. All right, and so the theorem we're going to prove is that this mechanism, as I've written it, satisfies epsilon delta dp, provided that epsilon is smaller than 1. So that this form for this definition of sigma squared kind of assumes that the epsilon you're trying to prove is smaller than 1. When epsilon is large, it takes a different form. But we mostly want epsilon small anyway, so this is not going to be like a big issue. Okay, so let's kind of look at the proof. And here's sort of the proof by picture. So if you fix two data sets and you think of the black curve as the distribution under data set X and the red curve as the distribution under data set X prime, then sort of the worst thing that can happen is that the red curve is shifted over from the black curve by delta, or delta, big delta, which is the sensitivity of the statistic. Now, if you just kind of stare at this, it sort of looks like the black and the red curve are close multiplicatively, but actually there's a region where the black curve is much, much bigger than the red curve in a multiplicative sense, and that region is when we're looking at very negative values over to the left. So what we'll see when we actually calculate these ratios is that the bad set are the ones where y, the outcome, is very negative. But as you can see from the way I drew the picture, the probability of getting those very negative outcomes is quite small. So probability bad will be smaller than delta, and that's what we want to prove. So to do the proof more formally, what we're going to have to do is we're going to have to actually calculate the ratio between the two curves, and we're going to have to figure out what is the bad region, or figure out some way of getting a handle on what is the bad region, and then argue that if I draw a sample from the black curve, the probability of getting in that bad region is going to be small. Okay, so what's going to follow is I'm going to do some algebra, and I'm going to plug in some calculations, but I want you to sort of have this picture in mind. That's really all we're trying to do. Oops, sorry. Proof is done. Oh no, where'd the proof go? Hold on. All right, we'll just do the proof on the fly. Okay, sorry about that. Let's copy this and get a new page. All right. So how are we going to do the proof? Well, let's start by, let's fix x and x prime. So these are going to be some neighboring data sets. And just to simplify things, let's assume that f of x is 0 and f of x prime is exactly delta, which is sort of the furthest from 0 it can be. It won't be too hard to see that kind of the worst case, right, is when you shift the red curve as far away from the black curve as possible. So now what we'd like to do is we'd like to understand the bad set. So let's look at the ratio, probability that the mechanism equals y over probability that the mechanism equals y on a of x. And because for Gaussians, everything happens in the exponent, it's going to be more convenient to take the logarithm of this probability. So, this is the thing we're going to do is we're actually going to, we're just going to try to prove that this logarithm is at most epsilon, which is exactly the same as proving that the ratio is at most e to the epsilon. But as you'll see in a minute, it'll just be easier to get rid of the exponents. Okay, so the way the Gaussian distribution is defined, this ratio is exactly e to the minus y squared over 2 sigma squared on top. And on the bottom, it's y minus delta squared over 2 sigma squared. Okay, so taking the logarithm, this becomes y minus delta squared over 2 sigma squared minus y squared. Okay, so if you don't follow this, take a moment to refresh your memory on logarithm rules. And now this is delta squared minus 2 delta y all over 2 sigma squared. Okay, and that's by distributing out the y minus delta to the all squared, and you'll notice that the y squared factors cancel out. All right, and now we defined sigma squared in a particular way, and the way we defined it was as the following. And if we kind of expand out and simplify, we're going to get the first term as epsilon squared 4 log 1 over delta minus y epsilon squared over 2 delta log 1 over delta. All right, so this is like a linear function in y. Okay, so this basically says, when is this thing bigger than epsilon? Right, so we want to know when is this bigger than epsilon, because that's exactly the set of bad y's. Okay, so the set of bad y's is exactly when this thing is bigger than epsilon. So here we can just do a little bit of algebra and see that bad is a subset of y where y is bigger than like negative 2 delta over epsilon log 1 over delta. Okay, so the bad set is maybe a little bit smaller. So basically, y is bad only if y is, sorry, it should be smaller. If y is smaller than negative 2 delta log over epsilon. But remember, y is drawn from a normal with standard deviation root 2 delta root log 1 over delta. Well, let me just write it this way. Standard deviation about delta over epsilon times root log 1 over delta. Okay, so it shouldn't be taking values that are much, much, much smaller than negative delta over epsilon. Right? The bad set is exactly the set where y has taken some extreme value away from its mean. And so that implies that the probability that ax is in bad is at most delta, which is exactly the thing that we want. Okay, so as you can see, the calculation's a little bit messy. You need to know some things about the probability that Gaussians take big deviations from their mean, but you can find those in the lecture notes, and you can work through the algebra and just kind of check that I set the parameters correctly as you're studying. But I think the intuitive thing to keep in mind is this picture, that there's this bad set, which is where we get a very small value, but the probability of that bad set under the black curve is not very big. Okay, so that's our summary of the Gaussian mechanism. So far, we haven't really established that it does anything that the Laplace mechanism doesn't do. But the nice thing about the Gaussian mechanism is that it generalizes well to higher dimensions. So let's take stock of what we can do if we want to output a query that is takes values not just in the reals but k-dimensional real vectors. And to do that, let's to get sort of a refresher on what we did to handle this case for with the Laplace mechanism. So with the Laplace mechanism, we defined the global sensitivity, which I'm now going to rename the global L1 sensitivity and denote it delta 1 because it's the maximum over all neighboring data sets of the difference between f of x and f of x prime in the L1 norm, which is the sum of the absolute values of all the coordinates of that vector. Okay, but I could also define the sensitivity in other norms. In particular, I could define it in the Euclidean or L2 norm, which is still the max over all neighboring data sets of f of x minus f of x prime, but now measured in the Euclidean norm rather than the L1 norm. And the Euclidean norm is the square root of the sum of the square of every coordinate. Right? And the reason that it's nice to think about the L2 sensitivity is just because it's often smaller. So the famous Cauchy-Schwarz inequality says that the L2 sensitivity is never bigger than the L1 sensitivity. But in turn, the L1 sensitivity can't be more than a square root of k factor bigger than L2. So intuitively, all this says is that the L2 sensitivity is never bigger than L1, but it can be much smaller by a factor of about square root k. And one important example to look at is where we have a set of k count statistics. So every we have a bunch of functions from the domain to 0, 1. And every function fj is just counting how many people in the data set satisfy that satisfy phi j. And f is just going to be the vector that kind of collects all k of these statistics and concatenates them together. So what we talked about in the last lecture is that the sensitivity of this f in L1 norm can be as large as k, because I could have changing one point in the data set could change every entry of this vector by 1. But the sensitivity of this function in L2 can only be root k. So it can be smaller by a square root of k factor. Okay, so good. We have a different measure of sensitivity that can be smaller than L1. But that on its own isn't so interesting. What's interesting is that we can, in fact, actually add noise proportional to this L2 sensitivity using multivariate Gaussian noise. So when I say multivariate Gaussian noise, what I actually mean is just adding noise to each coordinate of the vector independently from a normal. So a little more generally, I can call this is called the multivariate spherical Gaussian distribution. It's defined by a mean vector mu and a per coordinate standard deviation sigma. And the density is not so important until we start trying to prove things with it, but the gist is that this is some random variable z with k components z1 through zk, where each component zj is independent from the rest and is drawn from a normal with mean mu sub j and standard deviation or invariant sigma squared. Okay, so I'm just going to add normal to every coordinate independently. And there are nice bounds on the tails of this distribution. So for example, the expectation of the L2 norm of this vector is going to be about sigma times square root of k, and the largest entry in the largest entry in absolute value is going to be about sigma times square root log k. Right? And perhaps unsurprisingly, the theorem we're going to prove about this mechanism is that if we take some statistic f from u of n to r of k, to k-dimensional reals, and we add noise to each coordinate of magnitude of variance sigma squared, where the variance is proportional to the L2 sensitivity. So standard deviation in every coordinate is order L2 root log 1 over delta over epsilon. Then this achieves epsilon delta differential privacy. Okay, and the proof is a little bit technical, and it's detailed more closely in the notes, but what I want to indicate is it's really very similar to the case of k equals 1, which we studied in more detail with the univariate Gaussian. We'll use the same template. We can write out for a given y exactly what is the ratio of the probability that ax equals y to the probability ax prime equals y. And we can look at what conditions on y have to hold for for that ratio to be larger than e to the epsilon, and verify that we're unlikely to see such a y under a of x. So I'm not going to go through the proof in the lecture because it's a little more technical than I think is appropriate for a recording, but I'll say, see lecture notes. Okay, so to summarize, so that adding Gaussian noise to each coordinate, or adding a multivariate Gaussian, allows us to add noise where for each coordinate the noise is scaled to the L2 sensitivity rather than the L1 sensitivity. And we said that the L2 sensitivity can often be much lower than the L1 sensitivity. So let's see an application that kind of drives this point home. If I can find it. All my things are like way out of whack apparently. All right, I don't know what's going on. Oh, here we go. It's quite a night. So to go back to our application to releasing linear queries, if we have a set of k linear queries, then the Laplace mechanism, because the L1 sensitivity is potentially as large as k, the Laplace mechanism would add error k log k over epsilon. That would be the expectation of the error on the largest query, on the query with the largest error. Because the L2 sensitivity can't be more than root k, the Gaussian mechanism would have error square root of k log k times square root of log 1 over delta over epsilon. And so if you compare those things, if you ignored that log 1 over delta factor, the Gaussian mechanism's error would just be better. We would basically take the numerator and take its square root, so much smaller. The log 1 over delta factor means that this will only be an improvement over Laplace when we answer enough queries. And in particular, when k log k is bigger than log 1 over delta, we'll get an improvement. So that's what I wanted to say about Gaussian noise. It allows us to get better error when we're releasing queries or statistics in high dimensions. It has a lot of other nice properties. We're going to talk about composition in the next lecture, and then we're going to see how we can use it to train neural networks using gradient descent. So this epsilon delta definition is really useful and really a little more flexible than the basic definition of differential privacy. And we're going to be talking about it a lot in the coming weeks. So that's it for tonight. Thank you.